Now let us discuss tolerance stack-up analysis. We have already discussed what is tolerance stack-up analysis. It is stacking the components within available space. If we want to explain this in simple language, right? We have already discussed this. So it is way to find out minimum and maximum gap. Or in case of a part or a part, we can calculate the thickness, worst case thickness as well. This analysis is also called as gap analysis. By using tolerance stack-up analysis, we can optimize the tolerances, hence we can control the cost of a component. So that is why we generally go for tolerance stack-up analysis even at the part level as well. So why we use tolerance stack-up analysis? To get those following answers, right? In worst case, what will be the thickness of a tolerance sink feature, or what will be the worst case thickness of a particular feature in a component, right? If we want to decide that, we do tolerance stack-up analysis. To get the answer, will I be able to accommodate all the components in given space? If we want answer of this, we do tolerance stack-up analysis. Will the pin will fit within the hole or no? We do tolerance stack-up analysis. Why the interference coming after manufacturing, right? Once the component gets manufactured and it is not it is creating problem in assembly, we are not able to assemble it, then we do tolerance stack-up analysis to get exact idea what is going on, right? If we will reduce the gap, what will happen in assembly? If we want answer of this, of all these questions, then we do tolerance stack-up analysis. Right? What is the benefit of doing tolerance stack-up analysis? Benefit is it optimize the tolerances, hence cost of the manufacturing is being controlled over there. Avoid any kind of interference in assembly. That is the benefit of this tolerance stack-up analysis. Achieve required fit. Whatever we need, we have discussed the fits: interference fit, clearance fit, transition fit. So we can achieve whatever needed, right? We can troubleshoot existing design after the component got manufactured and have trouble in assembly. That is also the benefit of this tolerance stack-up analysis. We get exact result why this is happening, as we discussed in the first example, first case study, came and follower mechanism. Validate the existing design. So these are certain benefits of tolerance stack-up analysis. What are the driving factors? Generally, the driving factor is geometry or assembly itself, right? How the components are going to be assembled. We should have knowledge of that. Before doing tolerance stack-up analysis, we should have knowledge of assembly and its functionality. Then we can do it correctly. Here I am going to teach you a methodology. But if you are not clear about these two factors, it might be wrong. Even though you follow correct methodology, answer might get wrong because you haven't considered something that required to be considered, right? In tolerance stack-up analysis, the drawing itself is very important. How dimension a particular feature, how we choose particular dimensioning schemes and all, that is going to affect tolerance stack-up analysis. So drawing is also going to contribute a lot in tolerance stack-up analysis, and the geometry size of those component as well. So these are certain things that affects our tolerance stack-up analysis. Now, assumptions in a way doing tolerance stack-up analysis. There is only one assumption that we make in tolerance stack-up analysis, and what is that? In given drawing, the drawing is complete, and the dimension scheme like chain dimensioning, that mixed dimensioning, or the baseline dimensioning, whatever dimensioning scheme selected for a component, it is a best one, right? It is best for the design. So that is our assumption. Suppose I'm an engineer who is doing tolerance stack-up analysis. It may be possible that drawings are done by different peoples. I'm just doing tolerance stack up analysis. So that will be my assumption that drawings are correct. Best dimensioning scheme has been followed. Now, ways of doing it, there are certain ways to do it, like direct calculation, right? For a simple component, directly we can calculate. As we have already discussed, there is a pin of certain diameter and there is a hole of certain diameter. We can directly calculate whether this assembly is possible or not, right? Then if assemblies are there, many components are involved, we should follow a particular methodology that we are going to learn over here. And there are certain softwares as well, like 3D CS, Citol, even SolidWorks has its own version, and other CAD tools may be having this tolerance stack up analysis included as a add-on. So that is there, but what we are going to learn, that will be doing in software if we go through the software. So if you know the methodology that we are going to learn over here, you can easily incorporate that into these softwares. So that is the thing. So there is no certain way of doing tolerance stack up analysis. There are many ways to do it. So what should be the step to be followed in tolerance stack up analysis? First thing is we need to decide the objective, right? What is the gap, thickness or fit we need to calculate? So objective first, decide the objective. Then list all the dimension that is going to contribute to the gap. That is main thing we do. List all the dimension that is going to contribute to that gap. Then prepare the loop diagram and prepare the stack up table. Once we prepare the stack up table, we will be able to get max or min gap or maximum or minimum thickness. So in this way, if we follow these steps, we will get our answer. Define the objective, list all the dimension, prepare the loop diagram, prepare the stack up table. We can do tolerance stack up analysis by following these 4 steps. Now, what are the rules in tolerance stack up analysis that we are going to learn over here? So rule says loop can be vertical or horizontal, right? If we are preparing a loop, it can be horizontally left or right, or it can be vertical up or down. We cannot mix it that loop, one loop is vertical and one loop is horizontal. We cannot do that, though there is a 3D analysis, there is a possible we can use sine cos angle to decide that, but we are not going to learn that over here. We are going to learn for particular gaps, and we follow like loop can be vertical or horizontal only. So that is the thing. Loop should be closed one. So if we are calculating a particular gap, suppose this gap I am calculating, I will start my preparing loop from one end. I have to end it at other side of that gap. So in a way loop is closed. So anyhow loop should go like that. It starts from one end of the gap, it should end at other end of the gap. So in that way loop is closed. We will practice this, then you will get more idea. And another thing is to jump from, in a case of assembly, to jump from one component to other component, surface to surface contact must be there, or axis must be aligned. Axis must be aligned or surface to surface contact is there, then we can jump from one component to other component. Otherwise no. So surface contact is there or axis is aligned. So these are 3 rules. Loop can be vertical or horizontal. Loop should be closed, and to jump from one component to other component, surface to surface contact should be there or axis must be aligned. So in these scenarios we can do tolerance stack up analysis.